This talk actually, I started with a different title. It's I'm a phenomenologist, and I wanted to title it "How Does a Phenomenologist Design a Detector?" That is really what I want to convey. So I'm sure you've heard a lot about neutrinos, atmospheric neutrinos, and I guess you already know all about. Most of you are graduate students, I assume, right? Yeah, and anyway, you've had this really intense course, and from what I heard today, I think you've really learned a lot. So I want to look at things a little bit differently. Why is it that we look at things the way we do, and what is the physics that drives us to look at things in a certain way? And as I said, it's going to be a very relaxed talk, so I don't think there are any equations and certainly no derivations. It's just this very simple, kind of a different kind of view on atmospheric neutrinos. And since you've had lots of lectures on it, all the references, all the details, you can go and look up the other talks. I am not going to talk about it. So I'm going to start out with where do these atmospheric neutrinos come from? Of course, from cosmic rays. And then I will actually, once I've talked about the atmospheric neutrinos, I'll talk about how it has helped to look at neutrino oscillation parameters, and then some of the experiments. But all of this will be in a very generic formulaic way. I will not really highlight anything in particular. So let's start from here. So this is a picture which is very popular from SK. How do you get atmospheric neutrinos? So cosmic rays interact with nuclei in the air, where N is mostly nitrogen. So that's because our atmosphere is mostly made of nitrogen. And mostly what you produce are pions. Generally any meson can be produced. And these pions then decay to muons and neutrinos. And the muons further decay again, you can see, to more neutrinos, right? And already here you would have learned that in this chain of decay, you have two nu mu's and one nu e. So you get nu mu is to nu e fluxes of atmospheric neutrinos in the 2:1 ratio. I'm sorry I was not here for the other lectures. I'm assuming that you certainly know this to start with, right? So any deviation from this ratio, especially as a function of direction, which is a function of the path length traveled in the Earth, is a signature of neutrino oscillations. And I will keep asking this question, what about tau neutrinos? And the reason for that will become clear in a little while. So here are the cosmic ray fluxes. I've just taken it from a generic website. You can't read this because it starts from 10 to the power of 9 and goes to 10 to the power of 21 electron volts. So this is one of the most energetic particles ever to be detected. You can see each one of these are data points. I hope you can see, at least here you can see the error bars. So these are actually measurements. So, so all across here from, this is about a GeV, right? 10 power 9 eV is a GeV. And you can see that this goes over 30 orders of magnitude from 10 power minus 26 to 10 power 4 in units of flux, in units of meter squared per steradian per second per GeV. Per GeV occurs because this is d phi by dE as a function of E, right? So just to help us along, because these numbers don't mean anything to us, this energy corresponds to about 1 particle per square meter per second. So if I have a detector of size 1 square meter, then every second 1 cosmic ray particle will fall on it, and that energy corresponds to something like about 100 GeV. And even more particles will be there if you go to 1 GeV, and of course even lower than that. And these are the particles, so you can see that these particles will give you your pions and therefore muons, and I am just giving you a count of the cosmic muons. Typically, if you see one per square meter per second, gives you 3,600 events per hour. And as you go underground, which is where all neutrino labs are located, the flux falls with depth underground. So about a factor of 1,000 becomes less. You get about 4 events per hour. And the difference is that the neutrino fluxes don't fall with depth, right? Because they are not absorbed by the Earth's atmosphere. So the cosmic ray muons, as you go deeper and deeper, get attenuated. But the neutrino flux does not fall with depth. Unfortunately, the downside of it is that neutrinos are weakly interacting because the coupling constant is around 10 power minus 5. So instead of 4 events per hour, you will see about 1 event per day. So this is what you are trying to beat. So whenever you have a neutrino experiment, whether it's from this source or that source, whatever events you have has an unbeatable cosmic ray muon background, which is typically much larger. And different experiments have different ways of beating this background. So in between, I have some questions, which just to keep you awake, I want answers from you. So how do you detect these cosmic rays? I said all these are data points, right? No one? Haven't you heard of some balloon experiments? No? No one has been curious about how I can detect a particle which is so energetic and actually put a data point out there. So please go and look it up. These are all very fascinating experiments which have been going on also in India from the 60s actually. So I think you should look this up. Okay, so we now said that we have primary cosmic rays which are mostly protons all the way up to, what is the composition of cosmic rays? Does anyone know? Proton, helium, lithium, carbon, nitrogen, all the way up to which nucleus? Iron, very nice. Why iron? Most? I can't hear. One person? I still can't hear. I'm just deaf maybe. So let me just draw something on the board. Highest binding energy per nucleon, but there's something else very special about iron. All the supernova talks, because you did supernova, right? So if I write binding energy per nucleon, so it goes like this, and then it curves back, right? This is about 8 MeV, this is about 7 MeV, and this is about, so clearly I have not drawn a proper scale. And iron sits here, right? Silicon iron sits over here, right? So this is the end of the fusion process, right? This is why supernovae explode, right? You have hydrogen, 4 protons become helium, go on all the way up to iron, then no fusion can occur because the fission process takes over and iron neither does fission nor fusion, right? So that is the key thing about iron. So beyond that, you don't see such nuclei. All these, where are all beyond the iron nuclei produced then? In the supernova during the explosion, right? I don't know, since I didn't attend the supernova talks, I don't know what was talked about. So all the elements higher than iron are produced as the supernova is exploding. So that's where you get it from. So anyway, you have your primary cosmic rays, all these protons up to iron, mostly protons, come and hit Earth's atmosphere, as I said, and produce your pions. So now we have a question. Let's look at what is it that is being produced, why we keep talking about 2:1 ratio of nu mu is to nu e, and then I will design my detector depending on my understanding, right? So here I have pi plus minus pi naught, and the mass of them roughly the same. I've called it around 0.1 GeV. I should say 0.14 because the muon is 0.11, and therefore there is very little phase space available here. There is much more phase space available for pi decaying into E nu E. But the branching fraction for the electron channel is very, very small. The branching fraction for pi to go into mu nu is 100%. So why is it that E nu is so suppressed even though there is a huge phase space available? The branching fraction is proportional to mu squared, correct? But why is it proportional to mu squared? Helicity? You're almost there. Does anyone want to help him? He's used the keyword helicity. Yeah, come on. You have to wake up after lunch. And there is nothing new I can tell you about atmospheric neutrinos, so I can only tell you different things, right? Here, so what is it? You have a pion. What is the spin of the pion? 0, very good. So here I have, let us say, neutrino, and here I have, it will be mu plus, but I don't, okay, let's have mu plus. So I must have, angular momentum is conserved, right? So let us put spin is conserved, so spin must be 0. Plus half minus half, spin is 0, right? Now what do I do? This is a weak interaction, right? So it must be a left-handed interaction. So now here this has to be left-handed, this has to be left-handed, right? Now this is left-handed, right? Because you can see that helicity is minus, so let me put H as the helicity, minus, and I'm putting the chirality as left. Okay? Here also helicity is minus, chirality is left. But this is an antiparticle, right? An antiparticle means chi bar will be right. Right? So now I have a psi r which is being pushed into the helicity minus state, right? So how do I push it there? Chi r is 1 minus epsilon times helicity plus epsilon times helicity minus with some normalization factors, right? Where epsilon is m pi by e, sorry, mu by e. So what we say is that helicity is conserved, it's a good quantum number. I cannot violate helicity, but as long as the mass of the particle is not 0, a small fraction of the wrong helicity state is there in the antiparticle. And that small fraction is proportional to the mass. And when I square the matrix element, as somebody pointed out, I'll get gamma is proportional to m mu squared. If I had taken E squared, it would have been proportional to me squared, which is much, much smaller than mu squared. So the helicity suppression, so this is very important. This is why you have muons in the, if you had electrons in your cosmic ray, then they would have showered long ago and we'll have no background and life would have been very nice, right? But instead what we have is, because of weak interactions being left-handed, because of parity violation and weak interactions, because this is therefore suppressed, and you'll have, so in fact you can even put it, right? So now you know this is weak interaction. Gamma has to be energy, right? This is energy minus 2, this is energy plus 2, so this has to be times some number. I mean, you can even write the cross section, right? So this is the decay rate. This is the width of the decay rate. So it is getting suppressed, and therefore you're going to have, mostly you're going to have what production of mu rather than E. And that's it. Because of the mass of the pion being so small, you can't even think of tau, right? So let's go to the next spectroscopy. So, okay, here I've given the explanation. Let's not worry about it. Oh, I have a question here. What about energy momentum conservation? We said angular momentum is conserved, right? Helicity is conserved. By the way, helicity is a good quantum number, but it's not Lorentz invariant. Please remember that. Chirality is Lorentz invariant, but it's not a good quantum number. It can cause problems like this when you're doing weak interactions. What about energy momentum conservation? Is energy momentum conserved in this reaction? No one has any bets. Okay, how many people say yes? Nicely raise your hands. Okay, how many people say no? How many people are sitting on the fence? Most of you. Okay, should energy momentum be conserved always? Right? So why are you so puzzled? But what happens here? What is this process? Pi goes to mu, mu. Okay? What is the mass of this? Neutrino, what is the mass of this? Not roughly zero. It's not even a mass eigenstate. I cannot even talk about it. I don't care whether it is GeV, TeV, EV or milli electron volts, right? It's not a mass eigenstate. It can produce anything, nu1, nu2, nu3. You've learned all your oscillation physics, right? So if it produces nu1, then it will have certain energy momentum on the right hand side. If it produces nu2, it will have a different energy sum. If it produces nu3, it will have even different energy sum. But the initial pion had the fixed energy, right? So what happened to energy momentum conservation? Gone. I want you to think about this. I will not answer this now. It's a very important part of what you call decoherence in neutrinos. Okay, so this is something that will also play a role when you have neutrinos coming from far away like supernovae and things like that. So you think about it till the end of the talk. So let's go to the next meson. What is the next heaviest meson? K, right? K has a mass of about 400 and something, nearly 500 MeV. So here you are, look at the decays. Again, you'll always expect the decay to muon to be higher than decay to electron. You can see that. But now something new has happened. Because pions are 135 MeV and kaons are 500, Ks can also go to pi's, either pi plus, pi minus, or pi 0, whatever, K short, K long, all of them will go into hadrons. Why do they go to hadrons rather than all your other leptons? These hadronic channels are opening up, whereas pi was the lightest meson. There was no hadron it could decay into. So it can only decay semi-leptonically, right? Whereas here, and of course there's no baryon number because mesons don't have baryon number, but there are no lighter hadrons into which it could go. Whereas K can go into hadrons. So now there's a competition between leptonic and hadronic decay channels. And you'll see that that now forms a very important competition. So let's go to what is the next meson which will contain charm? What is D? What is the quark content of D? D meson? D plus UC bar, right? So mass is about 1.87 GeV. Now wherever I put 2 decimal places, you must ask why. Because I'm going to talk about tau neutrinos now. What is the mass of the tau? 1.777 GeV. So very little difference between the D and the tau, but still the D is heavier than the tau. Neutrino is practically massless. So you can see that there will be a small amount of D decaying into tau. And of course, you know that every lighter lepton must have even smaller branching fraction that we just discussed, right, because of separation due to helicity conservation. So the mu and E will be, so I've answered this question of Y. And now you look at this, anything going into mostly K, D going to K, so basically charm going to strange is about 100%. So you see, why are the hadronic channels taking over? Very nice, strong interactions. Strong interactions are stronger than weak interactions. Somebody finally named something nicely, right? So we understand why this happens. Now, after D, we go to DS. So that was a U C bar. This is an S C bar, right? So once I have S C bar, what do I have? Again, the branching into all the K, KS, etc. is mostly 100%. But now you see over here, I have a 5% branching of DS into tau nu tau. So it's only when I have about 2 GeV of meson that finally I'm opening up a channel for tau neutrino interactions. Why am I interested in tau neutrinos? Whenever we look at, okay, maybe since anyway you know all this stuff, the oscillation parameters will come later, but you know that theta 13 is small, right? Theta 13 is 9 degrees. This is the across generation mixing. 1, 2, 3 generations, right? 1, 2 is the solar problem. 2, 3 is the atmospheric neutrino problem, and that theta 2, 3 is about 45 degrees. So when you're looking at muons in the atmospheric neutrinos, muon neutrinos in the atmospheric neutrinos, you know that those mu's are mostly going to oscillate into tau, because mu to E is very small. It is suppressed by the theta 13. I'll show you the expressions later, okay? So what you really want to look at is, suppose the observed amount of muon neutrinos is suppressed, it could be that your flux calculation is wrong, right? Because fluxes are something that you measured, maybe what you measured, you are just assuming oscillations need not be oscillation, and cross sections though are just, your theory. So how can you believe it, right? So if you only see an appearance channel, then you are really going to be sure. So if you want to see and make sure that it is neutrino oscillations and not anything else, you must actually see these muon neutrinos oscillating into tau, which means you must see these tau neutrinos. So this is why we are interested in seeing where is it that the channel is opening up for tau neutrinos, and simply because tau is so heavy, tau is nearly 2 GeV in mass, you have to have production of very heavy mesons in your primary cosmic ray interaction with the Earth's atmosphere before you can even start to produce taus. Now you see the irony of it. Now you go to even heavier B. What is happening here? Oof, what happened? It just, because what is happening is that it's all preferring to go only 100% into your D, right? This is B going to C quark. Nothing is left over for your leptonic channel, and you are not going to see any. So there is a very, very narrow window for tau production in the atmosphere. It's essentially driven by DS and some small amount of wave mesons. So this is what we have to understand, right? When we are looking for atmospheric neutrinos, why are we looking for those atmospheric neutrinos? At what energy are we looking for those? Now we know. What we need to do is compute the cross-section for proton on Earth's atmosphere, some nitrogen, maybe nucleus, to give us DS. That will tell us how to compute. And DS, of course, will decay to tau. This is completely leptonic channel. And it will tell us how to look for, or what is the spectrum of the neutrinos that we are going to produce. So is this part clear? So, okay. Here is the flux actually. So you can see that I did a lot of search. I found 2 pictures. This is for nu mu and this is for nu tau. You can see that the label is different. They are from 2 different papers, but the x-axis are the same. They are from 100 GeV to 10 power 9 GeV. So same thing, 10 power 2 to 10 power 6. So it just goes up till here. It doesn't matter. This is what is of interest to us. And if you look at this, it's not visible here, but it says E cubed. And this also says E cubed. So you know that if you look at this first picture here, the cosmic ray flux actually falls as about e to the power of minus 2.7, which is around 3, e to the minus 3. So if you want to actually, and it's so many orders of magnitude, right? So it's much more convenient to talk about E cubed times, it's much more convenient to talk about E cubed times the flux. So both of these are E cubed times the flux. Some people will write E squared times the flux. So you have to find some, 2 things that match. But now you can see that the y-axis are very different. So this is, you can see at 10 power 2, you can see that the flux is of the order of 10 power minus 5 into 10 power minus 2. And here you can see that it is something like 10 power minus 6, 3 into 10 power minus 6. So it's about 4 or 5 orders of magnitude smaller. That is because production of DS is suppressed because of the huge mass of DS. Protons would rather produce pions than K, than D, than DS, than B mesons, right? So this is coming from the DS production and decay. This is coming from all the B quark production and decay. And so it is highly suppressed. Okay. Now, detection of these, of course, is even harder because this is just production part. Now you have to detect these neutrinos, but we know that neutrinos have only weak interactions. So whatever they do, however they interact in the detector, it can only be via weak interactions. There's no other possibility open for neutrinos. So for example, we know nu E goes to nu E. Nu E can hit a nucleon, do charge current scattering. So the L-type neutrino becomes the L-type charged lepton. Instead of having this is another nucleon, it can fragment completely into some bunch of huge hadronic states. It can do neutral current interaction. It can do many things. There's a further problem because of this detection where you come to tau neutrinos, because we know that m tau was nearly 2 GeV. So you must have at least that much energy of neutrino to produce the tau, because you must have nu tau n goes to tau something x maybe. So for nu tau goes to tau, the tau has to have at least 2 GeV of energy. But the 2 GeV is also not enough. Why is this so? We need at least 3.5 GeV of neutrino energy for this process to even start. Why is this? This comes from kinematics. See, this is something that, cross-section and kinematics is something that is very important consideration for all these experiments, okay? So this is a lab frame. So what happens is in the lab frame, because that nucleon is at rest, so the final state particles, neither of them is at rest. So you cannot produce tau at rest. In fact, what happens is that when you have 3.5 GeV, you will produce a tau which has about 2 GeV of energy. But below that, the threshold is 0. If you boost it back into the rest frame, of course, you will find that it will be, at 1.77 GeV, but you don't have that frame. You only have the frame in which this neutrino is coming and interacting with the nucleon, which is sitting at rest. So it becomes even harder. Why does it become even harder? Because again, the flux is falling as e to the minus 2.7. So by the time you come to 3.5 GeV, compared to 1 GeV, you are already 10 times smaller, right? So your cross sections are going to be even smaller. So your flux is small, your cross section is small, and so your taus are going to be a real challenge. So this is already something that we have learned just by knowing the kinematics and the cross section. Now, one mention I want to make is of directionality. Again, I'm going to assume that we know something about the detector, even though I haven't yet talked about the detector, because I want to finish off this aspect of things. So the directionality is highly dependent on cross section. So have you, I don't know, did you do anything on solar neutrinos? You learned something on solar neutrinos. So in super Kamioka and solar neutrinos, you did elastic scattering of neutrino on electron, right? Huh? Why don't we talk about it for atmospheric neutrinos? We keep talking about nu mu coming and hitting the nucleon and then becoming muon plus x or something like that, right? So why don't we talk about elastic scattering for atmospheric neutrinos? So again, it's dependent on the cross section. You see, if you take solar neutrinos, what is the typical energy of solar neutrinos? 10 MeV, 5 MeV, 10 MeV, and dead by about 20, right? So and what is the energy of supernova neutrinos? Around the same, right? So if you look at such low energy neutrinos, if you do elastic scattering on electron, that has a large cross section. Basically, what is a cross section here? It's like an area, right? So you're looking at something. Suppose this window, suppose had no glass in it, and I want to just throw the chalk piece, right? It's a very high probability that the chalk piece will go through. But if the window had a mesh, then and as the mesh becomes finer, the probability of hitting the mesh becomes larger and larger. That is the meaning of cross section. So what I want to do is I want to compare this energy with which the neutrino is coming with the inverse Compton wavelength of that electron. And when they mismatch, they will simply pass through each other and they will not see each other at all. So as the energy of the neutrino increases, it's not going to see the electrons at all in the water in Kamioka or in whatever experiment of yours. It's only going to see the nucleus. When it sees the nucleus, it will do coherent scattering on the nucleus. You give it more energy, it will do elastic scattering on the protons and neutrons inside the nucleus. You give it even more energy, what will it do? It will look at the quarks and do deep elastic scattering. Is this clear? So depending on the energy that you want to probe, the particular interaction that you're going to see becomes defined simply by knowing the cross sections for these processes. So before you even begin to build your detector, you must already decide, this is what I want to detect, this is the energy range I want to look at, this is the physics I want to study. And once you do this, for example, if I take Cherenkov radiation, right, this is how they saw both solar and atmospheric neutrinos in super K, right? How do you get Cherenkov radiation? What is the condition for Cherenkov radiation? I'm hearing lots of answers. I will be happy with that, but I don't really know what the answers are saying. So I will paraphrase it to say that the velocity of the particle must be greater than the velocity of light in that medium, right? So what is that velocity, for example, for an electron in water? Can anyone tell me what it is? What should be the energy of the particle if you don't know the word velocity? What is the mass of an electron? Half an MeV, right? At 1 MeV or 2 MeV, will I get Cherenkov radiation from a 2 MeV electron or 1 MeV electron? Is that sufficiently relativistic? Yes or no? Maybe. I don't know. How do we find out? Right? You have to answer this question. It's simple, right? What is the velocity of light in water? What is the refractive index of water? 4/3. Let's call refractive index 4/3 so that I can do round number physics. Okay? So come on, somebody do it in your notebook, otherwise then give me the answer, right? So refractive index of water is 4/3. So what will be the velocity of light? Velocity of light is 3/4 of what is normally c. So I'll just call c equal to 1. I hope that's okay with you. Huh? So how do we write this? So E is equal to, okay, let's write our relativistic equations. V is equal to P by E, right? This is your relativistic Einstein's equation. So what will I write this as? Root of, or let's write V squared. I don't know how to write this. E squared minus M squared by E squared is 1 minus M squared by E squared, which is 1 minus 1 by gamma squared. So 1 by gamma squared is equal to 1 minus, what is that? 9 by 16. Good Lord. Can I call this half? So gamma is of the order of 1.4, right? Which means if M is half an MeV, then if I say that E is 1 MeV, certainly it will match this, right? So 1, 2 MeV electron will give you Cherenkov radiation or not? Yes, right? What about for muon? Will 1, 2 MeV muon kinetic energy muon give you? No. What should it? Same, the formula is the same, E by M. So what is the mass of the muon? 100. So you should have at least 200 MeV muon to see Cherenkov radiation. Please go back and look at the Super K data. The original first atmospheric neutrino data of Super K, their first energy bin for muons is 200 MeV. And then you will congratulate yourself on solving this difficult problem. It's very important to know these numbers, because that's how you're going to actually look at a detector. So you're not just, somebody has given you a detector and you're doing a lot of GAN programming, but why did they design the detector that way? This is something that insight is very important, because at some point, you don't want to work on other people's detectors. You want to build your own, right? And for that, we have to be really clear about this. So this is where we are. So when we have even 2 MeV electron or just few hundred MeV muon, we're going to see Cherenkov radiation, and we'll be able to see this interaction in any Cherenkov detector. So either snow, which is heavy water, or light water, anything, whatever you have, you can do. Now this particular interaction I was saying about directionality, right? This is forward scattering. But of course, this cross-section for atmospheric neutrinos, as I said, is negligible. So let us not worry about this, let us forget about it. So let us go to the extreme of deep elastic scattering. Neutrino comes in, does charge current interaction, produces a charged lepton, breaks up the nucleon into some bunch of hadrons called X. Now in this, and here I am giving you the information because I'm not sure how many of you are familiar with cross sections. The average charged lepton energy is that is carried by the charged lepton is about half of the original neutrino energy. For antineutrinos, it's about 3/4 of the original antineutrino energy. So fully half the energy goes away in X, or quarter of the energy goes away in X, which means that you lose this energy information. I cannot look at the final state muon or electron and then tell what was exactly the energy of the neutrino that produced it, because half of it is lost. However, this cross section is forward peaked. We know that, right? We know that deep elastic scattering has a 1 by sin power 4 theta by 2 forward peak, severely forward peaked. For tau, it is essentially just forward peaked. There is no cross section beyond a few degrees. So we know that We have excellent directionality from deep elastic scattering, but we don't have good energy discrimination. On the other hand, if I look at quasi-elastic, so why is it called quasi-elastic? Once I have a charge current, the neutron becomes a proton or the other way around, depending on whether I have a nu or nu bar. So it's instead of just being elastic scattering, it's called quasi-elastic scattering. So what happens here? Here the charged lepton almost carries the entire neutrino energy because the recoil of the single nucleon is very small, but there is absolutely no direction information. In fact, there is forward, backward, every angle scattering is possible. So you have no idea where the neutrino came from. You know its energy very well. So now you see, you cannot have the best world. You have to choose, depending on what physics you want to study, you have to choose what processes you want to focus on. Right? So if you want energy information, then you look at quasi-elastic. If you want direction information, you choose DIS, and so on. Okay, if you want to look at low energy physics, you have to look at electron scattering. So this decides, this physics of cross sections decides what is it that you're going to see. So now, before we discuss, of course, the signals, let me just, for my talk, for the purposes of my talk, let me just list all the oscillation parameters, which you have seen in the last couple of weeks. So I'll go over it quite rapidly. So what we are interested in now is atmospheric neutrinos. And atmospheric neutrinos, atmosphere is all around the Earth, right? There's an atmosphere above us, and that is a true statement independent of where I stand on Earth, right? So because of that, at any given detector, the sources of neutrinos are from, I mean, not just above and below, but from whole 4 pi, right? Neutrinos are coming from, they are produced in the atmosphere below on the other side, they will come through the Earth and then get detected in our detector, or they are produced over our heads and directly come into our detector, right? So what is interesting is then to probe the density distribution inside the Earth as well. And this is the density distribution inside the Earth. And depending on what path length you have chosen, you will either probe the crust or the mantle or the outer core or the inner core. That's all I wanted to tell you, and that's about 12 to 13 grams per cc density in the center of the Earth. So without even going there, how do we know this, by the way? Prem gave it to us. How do we know this Prem profile? From seismic data, yeah. So we can also use the atmospheric neutrinos to probe the Earth matter effects. So due to matter-dependent oscillation probabilities, the reason I put this this slide first before writing down the oscillation parameters is I want to write an approximate expression for matter-dependent oscillation probabilities. And the reason is because these neutrinos will pass through the Earth and get affected by the Earth matter, and therefore right now I'm going to start by defining the probabilities in terms of matter-dependent Earth probabilities. And so these are the probabilities. Let's kind of, maybe I'll just show the entire slide. So here is where we are. So this is a very famous slide by now. I forgot to write, this is from the APS study. So there are two mass square differences. The smaller one, solar, the larger one, the atmospheric, and the M3 can either be the heaviest or the lightest state. But a combination of solar and reactor data tells you that, and beam data tells you that M2 is heavier than M1. So there's no doubt of. It's only M3 that we don't know. This is called the mass ordering problem. Okay. So if we don't know the absolute zero of the scale, the direct mass problem is this. And if the zero is very far away from these masses, then they are practically degenerate. So there is no hierarchy. But if the zero is very close to the lowest energy state, then these masses are very distinct and there is a well-defined hierarchy which is either normal or inverted. So that is the statement over here. I already mentioned that theta 12 is determined from the solar sector. It is around 34 degrees. Theta 23 is a 2-3 mixing angle which is practically maximal, but we don't know whether it is less than 45 or greater than 45. And the theta 13 is small, it's across generation mixing angle, about 9 degrees, but it's very important for it to be non-zero because only then CP violation is measurable. If theta 13 is 0, you can't determine delta CP. This is essentially the difference in the interaction of neutrinos and antineutrinos with matter. So this is also, some early measurements are there, but they all don't agree. So that's the status. So we don't know mass ordering, we don't know the octant of theta 23, we don't know delta CP. This is the open set of problems in neutrino mixing. So given that, what are the oscillation probabilities which are interesting for atmospheric neutrinos? So we have atmospheric neutrinos, electron and muon. Muon and electron in 2:1 ratio, tau negligible, negligibly small. And here I have put them in different colors, so let's go over them. I forgot to mention here that this quantity, when I write, sorry, capital delta, It stands for sine squared delta m squared 21 into L over E. That's what the delta stands for. So you can think of the mass square differences as the Fourier, what do you call it, partner of L over E, right? It's like sine omega t. Omega and t are Fourier complements of each other, right? So delta m squared is the complement of L over E. So that is in fact a very important thing that is being exploited by Juno, for example, to look at neutrino oscillation physics. And so M stands for the matter dependent terms, which I have given over here. So let's look at a few things. The leading term, if you look, since theta 13 is small, this term is small, this is cos theta 13, this term is large. So the leading deviation from 1 of p mu mu, that is the oscillation term, is proportional to 2 theta 23. So it's independent of octant. It is only sine 4 theta 23 that is octant dependent, and that is suppressed by the small theta 13. Okay. So the octant effect is a subleading effect. The leading effect is independent of octant. Whereas if you look at PE mu, then it is also suppressed by theta 13, and the only effect is actually proportional to octant. This is sensitive to the octant. And what are these matter dependent terms? Let us focus only on the theta 13 term here. The theta 13 can resonate to maximal when cos 2 theta 13 is equal to A by delta m 31 squared. What is A? A is some matter potential, and it is given as in terms of the matter dependent density rho in grams per cc and the energy E in GeV. And it is some factor which is some 10 power minus 4 times something. Okay. You can see that delta m squared is around 10 power minus 3. So if you have rho, this is 10 power minus 4. So if you have rho E around 10 or 15, then you will see that you will be able to satisfy this. However, depending on A, which is minus for antineutrinos and plus for neutrinos, either this equation, this equality of cos 2 theta and A by delta will be satisfied or not satisfied depending on the relative sign of A and delta. If you have the normal hierarchy, then delta is positive, and for neutrinos A is positive, so you will see resonance in the neutrino sector. Otherwise you will see resonance in the antineutrino sector. If you go back and ask your cross sections what they are doing, they will tell you that your antineutrino cross sections are roughly 1/3 of neutrino cross sections. So whenever you have to look at something in the antineutrino sector, you know you're already beaten by statistics. You're going to do a much worse job. So you have to keep in mind what you're hoping for. You're hoping for normal hierarchy so that you will see the effects in the neutrino sector and not in the antineutrino sector, right? So this is the hierarchy discrete, not hiring or odd. So now here we come to actual dependencies. Don't look at all the graphs. I'll tell you what to look at. So for example, look at the central thing here. This is now the dependence of probability on delta m31 squared. So let us say that we have central value of delta is 2.4 times 10 power minus 3. What happens if I reduce it to 1.8 in red or increase it to 2.9 in blue? Okay, you can see that the effects are very large, especially around 30 degrees. 30 degrees is the core crossing. This is when the neutrinos just brush through the mantle and start to enter the core. So the maximum matter effects will be seen at around 30, 31, 32, 33 degrees over here. Okay, so this is you can see that they will shift the density. So you can see that the minima gets shifted to the right, the red, the black and the blue, right? So this is how you're going to look at various ones of these dependencies. So this is the dependency with respect to theta 23. You can see again, it shifts it above or below 45. If it's in the first octet, it will shift it up. If it's in the second octet, it will shift it down. And there's a very interesting thing about delta Cp. This is for 2 GeV energy, this is for 5 GeV energy. You can see that here there is some effect of delta Cp, and here you cannot see any effect at all. So as the energy increases, your dependence on delta Cp is going to disappear. So if you're going to look at only high energies, then your entire atmospheric neutrino sector will be insensitive to delta Cp. It will be sensitive only to the hierarchy. If you look at only low energy atmospheric neutrinos, it will be insensitive to hierarchy and sensitive only to delta Cp. So this is where again you have to decide what is it you want to study. You want to study delta Cp or you want to study hierarchy, right? Something, okay. Sorry, where was I? So this is the background in which I want to talk about atmospheric neutrinos. So I'll start with super K. So this super K, I think everyone knows this detector. This is about 40 meter by 40 meter in size, about 50 kiloton, of which the inner detector is about 22 kiloton. And look at again the dimensions of this detector. The path length of photons, where are the photons coming from? Cherenkov radiation, right? In either pure water or ice is about 60 meters. So this decides. So if I have a huge drum which is about 100 meters in size, there is no point because the interaction will not reach the detectors which are all placed on the surface of the walls, right? So you have to know what you want to build, right? So what is it that these are the detectors which have some coverage, and on the top I have shown, it's not visible I think, on the top I have shown a muon Cherenkov light, and at the bottom I have shown an electron Cherenkov light, and you can see that here the inside is almost empty, whereas here the inside is almost filled. So this is how you distinguish between electron and muon. Why does this happen? What is Cherenkov radiation? What does it do? Electron, charge particle is going. Charge particle is going. Emits a photon. Emits a photon. Then what happens? Produces E plus E minus, which produces a photon like this, right? And what Cherenkov showed was, that's why it's called a Cherenkov cone, was that this entire radiation is contained in a cone of half angle 1 by beta, right? And therefore, it's very forward peaked. And if you have an electron, it does huge amount of Bremsstrahlung. So all these will be detected, right? So you have a filled cone, and muon is a minimum ionizing particle. There will be nothing inside. You will just see the outer layer. At some point, muon will also do Bremsstrahlung at much higher energies, right? If you have learned your properties of interaction with matter. So anyway, at the energies we are talking about, these are the two detectors, and this is what, as I said, you can see that this is, you expected to see no oscillation, but you actually saw not just oscillation, but as a function of, this is the upgoing events, these are the downgoing events. Downgoing events were almost not oscillated, upgoing events are oscillated, which means the long path length through the earth had something to do with the oscillation behavior. And this is seen even in higher energy muons, even higher energy muons, muons which went all the way through the detector. Everywhere you are seeing this. And this is the first, in fact, this was the first evidence for oscillation, although they got the Nobel Prize much later because people were not really sure about this. And on the other hand, they didn't see any oscillations in UE data. Now we know that that's because of the way the difference in the theta, P mu mu and PE mu. And now I go to ice cube. So ice cube also has, this is the central region is the core of ice cube in the middle, and it has these strings of photomultiplier tubes, and instead of water it is ice. So same thing, same, your photoelectron is going to travel so far, same detectors you're going to place all around, and your nu E is going to look like cascades, your nu mu are minimum ionizing, they're going to look like tracks, and the color coding just tells what came earlier and what came later. So why are the track shapes different? Why do you get cascade and why do you get track? For the same reason, right? Of what you saw in super K, right? So now I want to talk about tau neutrinos. So I forgot, I should have added a slide, I'm really sorry. So tau neutrinos have been seen in super K. They have more than 5 sigma evidence for tau neutrinos, but it is extremely difficult to see tau neutrinos. What is it that they will see? The tau will actually again decay. So you have nu tau, n goes to tau x, but the tau will decay hadronically because it's very heavy, so it will prefer to decay hadronically. So it will have long path length of huge energetic cascades, and that is identified as tau in super K. And in ice cube, there are very interestingly named processes. So the nu tau goes to tau, tau travels a certain distance, then produces a cascade, or it has produced a cascade, it has come from this thing and goes outside the detector, or it decays into, this happens 18% of the time, it branches into mu or E. So it can then give you a single ionizing particle, or it can do 2 lollipops, it can do many things. So each one of these is a very, very difficult process to see, and it is completely done through AI. So they have whole AI code which tries to match these things and see what happens. So all they need is that they have to have one length where the tau is simply traveling, and then it does something. Either it becomes a lollipop, or it becomes mu, or it does something, and that length for the energies that they expect is about 5 to 50 meters. So that's what their AI program looks at. Some track which is 5 to 50 meters long and then does something. So they have put a conservative cut of 10-meter length at least, and then they look at these events. And it was in the news recently, just last month or even a few weeks ago, that they have actually seen 7 events of these. You can see that this is blown up over here. 2 cascades, the first one for the tau production and one for the tau decay. And these 2 cascades are separated by at least 10 meters, which is what the requirement is. And all the energies sum up to something greater than 20 TeV. You think 20 TeV is very high, but you go back and look at your DS production process for taus, new tau, and you will see that there will be nothing from atmospheric tau, new tau production at 20 TeV. There is absolutely, there's not enough events at all to see. So where are these events coming from? They're coming from oscillation. So there are only 2 ways, either mu is going to new tau through oscillation, or new tau is coming from your DS decays. But if you go back and see your DS decays at these energies, there will hardly be not even 1 event, I think they expect. So here is the first time that they have found, I mean, although they say AI, but more direct detection than Super K, which had little more indirect detection, that they do see the new tau, which the new mu has oscillated into, and this is actually consistent with neutrino oscillations. So this is basically how, as I said, this is how you want to sample your various things. So every experiment has gone through this and decided how we can study this particular thing or that particular thing and optimize their detector in order to see such things. So of course, I didn't make a full list of experiments. Juno also claims that it can observe atmospheric neutrinos. If you remember what I said in the beginning, that delta m squared and L by E are Fourier complements of each other. So they want to separate the delta 3.1 and delta 3.2 mass square differences by looking at the frequency mismatch between the 2 of them. That is what they plan to do. For that, they need excellent energy sensitivity. They need to have an energy resolution which is better than 3% over square root E. And they are still looking at it, but they believe they've already built their detector and they are testing it, but they believe that they can actually reach that. Unfortunately, if they don't reach that kind of resolution, they will not be able to make this mass hierarchy measurement. So this is something that is very important. And of course, Juno can also observe these tau neutrinos. See, one thing I want to see, there are many neutrino experiments looking at various things. We saw also whether it's Dirac or Majorana, whether you have neutronoless double beta decay or not, or sorry, Catherine, which looks at direct beta decay experiment, right? To see the endpoint of the beta decay spectrum to find the direct mass of the neutrino or neutrino oscillation, whatever the physics. But for atmospheric neutrinos, you see what you have to beat that 1 event per square meter per second, which means you must have large detectors. So anything which says 70 ton, 80 ton, 100 ton, 200 ton, you can forget about all of them. They will not have sufficiently good quality atmospheric neutrino events. So large detectors such as Juno, such as Super K, Hyper K, all will be able to look at atmospheric neutrinos. And in fact, Juno can also observe the tau neutrinos, but I think they will not be able to do as good a job as IceCube. IceCube is just a fantastic experiment. IceCube also claims that they can detect the galactic neutrinos. See, in atmospheric neutrinos, the protons come and hit nucleons in the Earth's atmosphere, right? But there is our Earth is a planetary system inside a galaxy, and there are particles in that galaxy. So the cosmic rays can hit those galactic particles and produce neutrinos, and those galactic neutrinos, which will be because our galaxy is in the plane, right? We are in the plane of Milky Way. So you're going to see mostly the neutrinos will be coming from the plane, so in the horizontal direction. So they claim that they can also detect the galactic neutrinos, so it's an amazing experiment. So atmospheric neutrinos can also probe non-oscillation physics, though I didn't give any examples of that, but I think Raj spoke about that a little bit in the morning today. So although they have a huge range of energy and path length, which is why they can do so much different kinds of physics, they have a particular disadvantage with respect to beam experiments, because in beam experiments, like for example, if you take Dune, then you know the direction and spectrum of the neutrinos. You know the path length exactly, you know where your accelerator is sitting, you know where your detector is sitting, You know absolutely the spectrum of the particles that you have produced because you are producing it either through muon decay or pi decay or whatever process. So at least if you don't know the individual energy, at least the spectrum is very well known. So for example, if you see a particle which is coming at an angle theta with respect to the beam direction, you know that the initial neutrino came from that direction and the scattering was at an angle theta with respect to it. Here, if I see something with respect to an arbitrary theta with an arbitrary XYZ choice of coordinates, I don't know where the original neutrino came from. I only have a scattering angle with respect to some unknown initial direction of neutrino. So that precision I can never have, which I can have with beam experiments. On the other hand, beam experiments are single path length experiments. And it is very difficult to find a beam experiment which goes through more than just the crust, not even the mantle. I mean, maybe, you know, just touches the mantle or something like that. In the olden days, about 10 years or 15 years ago, people were talking about neutrino factories with path lengths of 7,000 kilometers, magic baseline and all that. That also would not have gone through the core. It would have just gone through the mantle. So it's very, very hard to go through the core. You have to really work very hard. So that way, I think in the sense of being able to probe also parameters of the earth and, you know, earth tomography, which I'm sure somebody would have talked about, they have great advantages. But on the other hand, if you want to do precision physics with them, then there are certain things which beam experiments can do better. Of course, I would not like to end without saying an experiment was proposed in India to study atmospheric neutrinos. Now we know that we have to find the mass hierarchy. We have to see whether the matter effect is in the neutrino sector or in the anti-neutrino sector. So what better to do than to actually separate neutrino and anti-neutrino events, which you can do if you separate mu plus and mu minus events, because neutrino will produce mu minus and anti-neutrino will produce mu plus. So you have a magnetic field, separate the two. It is a very nice idea. A lot of work was done. Unfortunately, this experiment has not come to pass. I think we learned a lot of things from it. So let us put it down to experience and move on. But I still feel that there is a lot of physics, a lot of nice things to learn with the atmospheric neutrinos, and I'm glad that other experiments are looking at them. And especially I think in the tau sector, because finally we're looking at appearance experiments. So once and for all, you're going to say that, yes, this is actually neutrino oscillation. It's not just that nu mu disappeared, but actually it reappeared as nu tau, and that is what we are measuring in the detector. So that is something I think very, very important that we can get from atmospheric neutrinos. Of course, there are many, many experiments, as I already said, and I think there are practically 100 small and big neutrino experiments, and its importance is because it is the only signature so far of physics beyond the standard model that we have found. We have a lot of evidence for dark matter. We have zero evidence of particle dark matter. That is, we don't know that dark matter is made up of particles. We have no idea. We have absolutely no indication. We only have some gravitational properties of this matter, and we don't know whether it has particle nature or not. So neutrinos, neutrino masses and oscillations is the only physics that doesn't fit into the conventional standard model of particle physics, and that's why there is so much interest in it. And so I apologize to all aspects of atmospheric neutrinos which were not covered here, but not really, because I think you learned all about it in other talks. So thank you very much.
Any questions?
Hello. Yeah. So here you said that Juno can have like tau neutrino appearance. So they have given some numbers like or events spectrum for that what energies they are expecting or something.
Let me see if I've given a reference. I have not given a reference. I can send it to you. So it's, of course, they are just doing the calculations. There is no data which is being analyzed yet, right? But so what they have is there is only one thing that can be said about tau. See, tau behaves more like a hadron. See, tau has a mass of nearly 2 GeV. Tau is heavier than charm. In fact, tau is very close to charm mass. Charm is 1.5 GeV. This is 1.8 GeV. So your biggest background for tau will be the hadronic decay modes of charm, which you have to do something about, because you know that will appear in deep elastic scattering. Although because nucleons don't really contain that much charm, that will be suppressed. But on the other hand, our tau is also suppressed. So that is a feature. I'm not sure how Juno is going to deal with that. Because of the energy range that IceCube has, they get past all this. See, they are allowing for 10 meters gap and cutting out, they have a huge number of events, I'm sure, with 5 meters and 2 meters gap between your two cascades. But they can afford to cut it all away because they are a huge experiment. So, but I'll send you that paper reference if you send me your email address. So Juno also says that they can do this through this cascade path length. So that's what even Super K has done. Super K has looked for long tracks and identified them as mu, but sorry, as tau. But they didn't do any AI-based particle identification, which IceCube has done. So IceCube, I think, is much stronger basis simply because of the kind of analysis that they have done. And of course, they have done it in the more modern generation where people are using AI for many more things, and Super K data is much older and they didn't do it that way. But Juno says that they can do the same thing, look at cascades, and they are a big enough experiment, they can also see it. So they have claimed definitely that, I think in TAUP 23, I think there is a presentation by them. I will send you the reference. Okay.
Hello.
So as I said, you need to be large. Once you are large enough, then you will see these things. Well, that's what it seems to be, right? That's what it seems to be. See, it's not just that. Let me be a little cautious about that. See, for example, we looked at tau production in that is new tau detection in INO also. INO is an ion detector. Ion detector, all cascades die very quickly, right? Because you're not going to see them go 10 meters or 20 meters. Only muons do that in ion. So you cannot really say that everything which can have large enough things so that large cascades will see tau. You will see tau even in INO, but I mean, if it ever gets built, but that's a different matter. But theoretically speaking, you will see it, but not because of path length, because of certain other characteristics. So it's not in general true that you just need to have a detector for large cascades. It depends on the nature of the detector. Here, this is just water, right? So everything just goes through. I mean, in ion, these things, electrons and cascades will not travel very far in ion. So let's be a little cautious about statement, but that in general, yes. Typically, the idea, and you here the charge identification will not help you. Neither for tau nor for electron, because there's so much scattering and so much of Bremsstrahlung that you're not going to see any no bent tracks of electron, nothing like that you will see, right? Or of tau. But in general, yes, if that's the kind of detector, if you don't have a segmented detector or some very light Z material, then yes, it is true that if you can build a long enough path or track, then you will be able to see this separation of cascades. Or even if you can't see the separation of cascades, extra long cascade, where you know that the muon or the electron flux has already decayed away, because the cross sections are falling, right? So
We have one more question.
Yes, ma'am. In the second point, what do you mean
so
by...
who's talking? Sorry.
sorry. In the slide, the second point you have mentioned consistent with neutrino oscillation. Could you explain what you mean by that?
So the statement is the following. That's why I went through that whole initial part, right? Here you have this is your D meson production. And just like you have the pi goes to mu nu, you will have ds goes to nu mu nu tau. You can just take that same equation and replace mass of the muon by mass of the tau. Okay, so that is the same process. That is your fragmentation. You know how many nu taus you're producing in the atmosphere. If you look at this, okay, so where is your TeV? 10 power 3 GeV is TeV, right? So this is where you are. So this is the amount of events you expect, which is kind of zero. So you won't expect to see any events which are just coming from this negligibly small tau neutrinos in the atmosphere produced because of ds decay into tau. However, they saw 7 events, and those 7 events are much larger than the zero expected background. So where are they coming from? So they are coming from the fact that the nu mu has oscillated, in the nu mu in the atmosphere has oscillated to nu tau, and that is large. Why is it large? Because it is determined by theta 2,3, which is maximal. So half the nu mu are actually gone to nu tau. So although you started out with 2:1 ratio of nu mu is to nu e in the atmosphere, for the events which are coming from below, you actually have 1:1:1 nu e, nu mu, nu tau, because half the nu mu have gone into nu tau. But because nu tau producing tau is suppressed because of the cross section, because tau is massive, you will find only few events, and these are the few events they have found. So one, they have found 7 events, which means they have found tau events, which means there have been nu tau events seen in the detector. But this number of nu tau events, 7, is much larger than the expected background from direct nu tau in the Earth's atmosphere. So these are coming from neutrino oscillations. Is that okay?
I think those 7 Newton candidates are actually astrophysical neutrinos. Those 7 candidates
See,
are
they cannot distinguish between, as I said, galactic neutrinos and atmospheric neutrinos.
Yeah,
but if you look at the spectrum of atmospheric and galactic neutrinos, they are roughly of the same order. So where they come from, they will not be able to tell.
Yeah.
But even if you put the 3.5 of those events should have come from atmospheric neutrinos, all of them could not come from galactic neutrinos. That I am very sure of.
I think in the analysis they have considered the atmospheric neutrino as a background, and these 7 neutrinos are access to that background.
Yes, but they have not sure whether it is coming all from galactic or atmospheric. And I should have put that graph 1 second. I didn't put that graph, I think. Let me just see if I put that graph. Where is it? I didn't put that graph. Okay. If you see if you look at the galactic neutrinos, they will come somewhere like this. They will come like a bump like this. Okay. So they will end around 10 power 6 or 7, I think. And they will come like a bump, but they will be below the ds. Okay. They will be below the ds. They are not above the ds. This paper has 1 second. No, this paper will have it. This Okumura's paper, you just check that paper. He will show the DSB and galactic source of neutrinos. Okay, you will see that they are smaller. So it is actually coming from. They are not sure whether it is 6 or 7 also. It is small. Number is small. I think by the end of this year they will clean it all up and they will give you the right numbers. But the fact that they have actually seen tau neutrinos, I think that is for sure. These events are certainly tau because, see, even I can see, I am not an experimentalist, even I can see the 2 cascades, right? So there are tau neutrinos and source of them is not very clear, right?
Ma'am,
yeah.
actually what Krishnamurthy is saying is both of you are true. The first analysis is
that is a very, very diplomatic answer. Tell me what is the fact.
The first is that over the atmospheric neutrino background, how many events we could have expected over this 10 years of data?
Correct.
That comes around to be 10. Then the second analysis, what they have done, they went back to the data and they tried to find out those 10 events in that data sample. They found out that 7 astrophysical events which coming from not from the atmosphere, directly pointed out from the source.
I see. Okay.
So they found the sources also. The first part of the analysis is just the way you said it.
Oh, okay.
Over the atmospheric background, there was a possibility of around 10 astrophysical tau neutrinos might have been seen in the tau in the ice cube detector. Later they found out, they have seen 7.
Oh, okay, I see. My mistake. Then I stand corrected. Thank you.
Yeah, I had the same question, but I would have a follow-up to this. So when you are talking about prompt neutrinos, prompt neutrino flux, so at high energy the flux is high for it is more than the conventional flux, right? For prompt at very high energy.
I don't understand what you mean by high. I mean
high energy, when I'm talking
by the
about.
way, as I told you that this is not increasing. No, please understand this is falling very fast.
Yeah, I do understand, but at very high energy, I'm talking about in the astrophysical neutrino sector, like in 20 TeVs or so.
Yeah.
So we cannot clearly distinguish between whether it is astrophysical neutrino or.
No, but that is the difference. No, see, the thing is, if you look at galactic neutrinos, see, astrophysical mostly are galactic. From outer this thing, there are very, very even fewer because the flux falls as 1 by r squared, right? So if you have galactic neutrinos, they will be in-plane neutrinos. So they will be coming from the horizontal region. So in fact, the horizontal flux is in fact what everyone even plots. I mean, when people are plotting galactic neutrino spectrum, they plot the horizontal galactic neutrino spectrum because our galaxy is a flat object, right? So in ice cube, that will be a very different signature. So you know from the direction, that's why I talked about directionality, right? If it is coming from the atmosphere, then we know that there is a window. I mean, it's not as though everything coming from 90 degrees is tau. We know that the maximum nu tau oscillation happens in a region from 0 to about 50 degrees, vertical, around the vertical direction. But the galactic neutrinos are coming from the horizontal. So we know that they are coming from different directions. And there is enough directionality in this so that they know the difference between these two. Of course, there will also be something from the horizontal direction, but horizontal direction you see, what is the ice cube detector is about 1 kilometer underground, which means that in the horizontal direction you have about 1,000 kilometers of rock. In 1,000 kilometers of rock, you will not find many tau samples. So if you have horizontal events, 100% that it will be galactic neutrinos. If you have events coming from below, or as I said, in the cone of about 50 degrees, okay, you will find that there is a maximum around 45-50 degrees. Then you will know that that is coming from atmospheric neutrinos. So there is no confusion between the two. It's just that the data set is small, and as I said, I think maybe I'm mistaken now in how I interpreted the data, but surely they will find atmospheric neutrinos, and surely they will find galactic neutrinos, because at this 10 TeV, 20 TeV region, the two fluxes are of the same order of magnitude. Unfortunately, I have it on my machine. I can show it to you afterwards. But of the order of magnitude, those two fluxes are the same. Within a factor of 2, they are the same.
I just wanted to know that as far as I know, that prompt neutrino flux, prompt neutrinos has not been yet.
What do you mean by prompt neutrinos?
This prompt neutrino flux, which is coming from D mesons,
right? The source is prompt, yeah, sure.
Yeah.
Prompt neutrinos just means coming from D. D is very small. D fraction is 10 power minus 3. This is ds, right? This is the green is ds. Okay, your prompt is sitting more here, right? So if you look over here, right? See, where are we? We are at, this is GV, right? We are at about 10 TeV. So we are around here, right? Can you see this line? So this is where we are, right? Yes. So this yellow line, whatever, is your D plus. Your green line is your ds. This is your lambda something, so you don't have to worry. This is, so mostly everything coming from pi. Just forget everything. Everything is coming from pi. Right over here, everything is coming from pi. This is mu, right? The first order of this thing, everything is coming from pi. No one has been able to tell whether you're getting contribution in mu from k, d, whatever. That will come at much higher energy. Because who has looked at mu flux, super K? What is super K energy? It is just about 1.3 GeV, that's all they can see. Beyond that, they call it high energy muon, non-stopping muon. Up to about 1.5 GeV is all they can do, right? 1.5 GeV is sitting somewhere here. This is already 100 GeV, right? So the neutrinos that have been detected, the muon neutrinos that have been detected at much lower energies, right? Super K cannot see beyond 1.5 GeV. See, a machine which can also see 5 MeV solar neutrinos, that it can see 1.5 GeV atmospheric neutrinos, already big thing. So it cannot see this 100 and whatever. So 10 TeV, this is 1 TeV, this is 10 TeV, right? So this 10 TeV it cannot see. It will not know at all what those new mu sources are.
In the y-axis, it is phi into energy cube, right?
Yeah. It's so, E cube. Both of them are E cube. E cubed phi. This is also E cubed phi.
So I'm just saying that at very high energy, you can see the coinciding thing, and one of the...
Yeah, but no one has measured here, no new mu spectrum here. All the super K is here. Super K is at 1 GeV. This is 10 power 2 GeV, right? This is 10 power 1 GeV. This is 10 power 0 GeV, right? So super K has seen here, somewhere here. This is the muon flux. This is the tau flux. That's all I'm saying. Surely if you can measure around here, you will definitely see all those components. In fact, see, the one very interesting thing that you can see at 1 TeV is that you won't see just the mu fluxes. There is something called the charge ratio even in the pion and muon cosmic ray spectrum. The pi plus is slightly 10% more than pi minus, and that ratio changes as you produce more starting from K, because when you have Ks, it will produce pi plus and pi minus asymmetrically. It will produce pi plus and pi naught. It will not produce pi minus. So there are experiments, even Super K has seen, and Minos has also seen data at around 100 GeV, 1 TeV. 1 TeV is here, right? So 100 GeV to 1 TeV, they have seen that the charge ratio of this pi plus, pi minus changes according to this distribution, how the pi versus K distribution occurs. But how that translates into the new mu flux, no one has seen. See, mu flux is one order of magnitude, many orders of magnitude harder than the original pi or mu flux. Right? So this has been seen in the cosmic ray muon flux. It has not been seen in the atmospheric neutrino flux. Okay? So certainly they have seen the change in the ratio. So between 10 GeV and about 800 GeV, you can see that the charge ratio increases from 10% to some 30 or something like that. And that is coming because of the K channel opening up. But in the neutrino sector, this has not been seen. We just put it all together. Honda has given us the fluxes coming from all sources. His cosmic ray model has been validated against balloon data, various things, and then we just let it go. No one has this distribution yet for atmospheric neutrinos. But they have it for the muons, cosmic muons, yes. Difference is clear?
Okay, let's thanks Professor Indumathi.